All right, so today we're going to look at solution sets of linear equations. Basically, we're going to look at different types of solutions. We kind of already talked about the general form of a solution. When you row reduce a matrix, sometimes we get these free variables, sometimes we get the no solution case. But we're going to dive a little bit deeper in this section. Now, oops. Let's start out by just finding the solution to this matrix equation. Now, we know this matrix equation is equivalent to a system of linear equations. We know that this matrix equation is equivalent to the vector equation. So find the solution to this matrix equation. Go ahead and push pause on the video and try that out. All right, so hopefully we remember how to do this. The way we've been doing it so far, in order to solve this equation, we create the augmented matrix, where the augmented matrix has this matrix here as the first three columns, and then the fourth column will be our constants column. Row reduce that. If you go ahead and do that, let me pull up what I did. So create the augmented matrix, then row reduce it, put it into row reduced echelon form, and you come up with this matrix here. Now remember that these columns stood for the coefficients of x1, the coefficient of x2, coefficient of x3, and then equal to the constants. So what that first row is saying is that x1 plus 2x3 is equal to -5. That second one is saying that x2 plus x3 is equal to 4. And that last row, well, technically, I should say, noticing that the x3 column is a free variable means that x3 is some sort of free variable. Okay? And when we rewrote that by just subtracting 2x3 from both sides, subtracting, x3 from both sides of that second equation. All right, this would have been the general solution to that matrix equation. So the matrix equation has this as the general solution. All right. Now what we're going to do is we're kind of keep that in the back of our head. Finding the solution to a matrix equation, we row reduce echelon form the augmented matrix. And we're going to keep that general solution back in the back of our head because we're going to revisit that in just a moment. But first, we're going to look at homogeneous system of linear equations and a homogeneous matrix equation. Okay, homogeneous just means that the constants are all 0. Okay, so a homogeneous matrix equation is a matrix equation that looks like matrix times vector is equal to the 0 vector. When you have linear equations, it just means the constants are all 0. So if you're thinking about creating an augmented matrix, basically that right-handmost column is going to be all zeros. So homogeneous means that your output vector is the 0 vector. Okay. Now, clearly, there is one obvious solution to the homogeneous equation. All right. If you want to multiply a matrix times a bunch of coefficients. Think of the vector equation. What coefficients could you use on each of these column vectors to give you 0? Well, the obvious answer is, what if we made all the coefficients 0? In other words, what if we made x be the 0 vector itself? So since any matrix times the 0 vector is going to give us a 0 vector, the 0 vector is always going to be a solution to this homogeneous equation. Okay? Now, because it's the obvious one, we call it the trivial solution. So the 0 vector is the trivial solution. The interesting case is, are there any non-trivial solutions? Are there any vectors other than the 0 vector where if you multiply it by some matrix, it gives you 0? All right, so we're going to be looking for non-trivial solutions to the homogeneous matrix equation, or in other words, non-zero vector solutions to the vector equation, non-zero, not all zeros, for our variables in a system of linear equations that is homogeneous. Okay? By the way, notice that we already know that one solution exists to this equation. So if we can find multiple solutions, we know that, again, any system of linear equations only has 3 options: no solution, one solution, infinitely many. So we know a homogeneous equation is either going to have one solution or infinitely many. So if we can find non-trivial solutions, there's going to be infinitely many of them. Okay? And think of this in terms of free variables. Okay? Just like we saw on our previous example, although this was not homogeneous, we had a free variable, and therefore we ended up with infinitely many solutions. Okay? All of them were this form. Now, when we have the 0 vector as our outcome, things will be a little bit different, but that's the basic idea there. Okay, so infinitely many solutions means free variables. Anytime we can find a non-trivial solution leads us to the infinitely many solutions case. So essentially, we're looking for free variables. Now, let's do this. Let's find the solutions to the matrix equation AX equals 0, where A is this matrix here: 1, 2, 4 as the first row, negative 2, 6, 2 as the second row, 6, negative 8, 4 as the third row. And once we find solutions to that matrix equation, remember there's at least going to be one, hopefully there's more, we're going to write the solution in the general form. So I want you to push pause on the video and try that out. Find the solutions to the homogeneous matrix equation using this matrix here. Okay, hopefully you went ahead and did that. I'm going to get back in the swing of things here. So we go matrix equation, AX equals 0. And the augmented matrix would be this matrix with an added column of zeros to the right. So if we were doing this, let me go back to the Word document. We'd taken the matrix A, and then since we have to equal all zeros to be homogeneous, we'd have an augmented matrix that has the last column be all zeros. Now notice that when you put that in row reduced echelon form, you get out this. And it shouldn't surprise us that the right-hand column is still all zeros. So a lot of times when people deal with homogeneous matrix equations, they just lose that right-hand most column because they know that no matter what elementary row operations you use, you end up with just a right-hand column of zeros. Elementary row operations are just doing linear combinations of zeros, and linear combinations of zeros end up as zeros. Okay? Now, if we were to write the general solution to this, x1 would be equal to negative 2x2 plus 0. I'm sorry, I mistook that. Negative 2x3. x2 is equal to negative 1 x3, and then x3 would be free. All right, so that would be the general solution to that matrix equation. Now, what we're going to do is we're going to introduce a new form, a new way to write the solution to the matrix equation. And so we're going to go from listing out what each entry is to write out a typical vector that would be the solution to that matrix equation. And so what we're going to do is write out a typical vector as a constant times some vector plus a constant times another vector. If we need to, plus another constant times another vector plus another constant times another vector. Okay? So in parametric form, the solution set is going to be constant times a vector. So let's go ahead and do that with the matrix equation we just solved. So we just solved the matrix equation AX equals 0, and we're going to write our solution now in parametric form. Okay, what I like to do when I do this, I think general form is very straightforward. So a lot of times what I'll do is I'll write the general form first, and then from that, extrapolate to the parametric form. Okay, whoops. So here's the general form. All right, so we have our general form solution right here. And we want to create a vector form. Now, here's what we have to notice, that x3 is a free variable, so I can make it whatever I want. I'm just going to call that for right now x3, okay? Now, what is the first entry of a vector going to be? Actually, maybe I'll think about it like this. Instead of thinking about constants out front, let's think about it like this. x1 represents the first entry of the vector. So x1, whatever it is, can be written as negative 2 times x3. The second entry of my vector is going to be negative 1 times x3. And the third entry of my vector, well, it's whatever I choose x3 to be. So the third entry is itself just x3. All right. Now that's not quite parametric form. What we'd like to do is we like to rewrite this as a variable out front, which we're just going to call x3, multiplied times some vector. All right, so variable times a vector. And in order to get parametric form, all we have to do is take the coefficients of what the x3s are. So that's what parametric form is. Parametric form in this case would just be this vector. Now sometimes, like always, you can put the variables in front, you can put the variable in back, but that's it. A typical vector multiplied times variable. That's the parametric solution to the matrix equation. All right, and you'll notice in parametric form, what's going to happen, we're always going to have a variable times a vector plus maybe another variable times a vector. These variables are going to be the free variables. So the S and the T are going to be representing the free variables in when we row reduce the matrix. All right. So I'd like you to try this one on your own. All right. Find the solutions to this matrix equation. Try to write those solutions in the general form and then also in parametric form. Hopefully you went ahead and did that and got both the general form and the parametric form. Let me go over that real quick for those who haven't. Now, basically, we have our matrix A as 1, 2, 7, -2, -4, -14, -1, -2, -7. I'm not going to list this out as the augmented matrix. I'm just going to list this out as matrix A, but we know that there's this column of zeros on the right if we're thinking the augmented matrix version of this. It's just kind of a waste to put that column of zeros, so I just leave it off. Now, when you put this matrix into row-reduced echelon form, you're going to end up with this. Now, the general solution to that is that x1, well, let me write it out this way. x1 plus 2x2 plus 7x3 is equal to 0. That's what that first line gives me. So if I'm subtracting 2x2 from both sides, if I'm subtracting 7x3 from both sides, what you end up with is that x1 is equal to negative x2, negative 2x2 minus 7x3 plus 0. We don't have to add the plus 0 in. And what's that mean about x2 and x3? Well, because x1 was the only column that was a pivot column, since x2's column and x3's column both are not pivots, x2 is a free variable and x3 is also a free variable. Now, if that is the general solution, so general solution is that each entry has to look like that. Now think about what this means for a vector. A vector is going to have to, first off, have 3 entries. The first entry is going to be negative 2 x2 minus 7 x3. The second entry is going to be the x2 entry. And the third entry is going to be whatever you choose for your x3 entry. Okay? So that's what it's going to look like. Now, this is not the parametric solution. The parametric solution needs to look like variable times vector plus variable times vector plus variable times vector. Here we have 2 variables. Okay? So for each of these variables, for each one of the free variables and specifically, we're going to create a vector. So we're going to create a vector for x2 to multiply by. Should be fairly straightforward. What vector that's going to be, it's going to be all the coefficients of x2. So negative 2 in the first entry, 1 in the second entry. And notice x3, this third entry, doesn't have any x2 involved, so we just hit a 0. And then we're going to do the same thing with the x3. The x3, if I were to create a vector which has the correct coefficients, it would be -7 as the first entry, 0 as the second entry, and 1 as the third entry. So this, let me highlight that real quick, is the parametric solution, all right, to the equation. Again, I'm kind of writing in middle steps, but once you get good at this, you'll go immediately from here to here. You'll say, oh yeah, -2, 1, 0 are the coefficients of x2, -7, 0, 1 are the coefficients of x3. So we write our parametric solution like that and move along, okay? And that's always going to be the case. It's always going to be the coefficients of your free variables are going to be the entries in your vector, and then you just let the free variables themselves be the variable component. Okay. Some people, by the way, like to change these from x2 to x3, from x2 and x3 to like some other variable like s's and t's, but we'll just keep it as x2 and x3, make it simpler, a little bit more straightforward. Okay, so that was that example. Now I want you to push pause. I've already row reduced A for you, but I want you to think of what the general form of the solution to the matrix equation would look like, and then what the parametric form would look like. Push pause on the video and figure both of those out. Once you do that, unpause the video and check your answer. All right, so hopefully you went ahead and did that. We're gonna move on and create this. So we already have it row reduced for us. Okay, we have it row reduced for us. It's equal to that. Now, remember, this is just the A part. So there's also, again, this implied column of zeros over here for the homogeneous system. Okay, there's this implied column of zeros sort of to the right that we just don't have to write down. So what this would say is x1, I'm actually going to solve this. Once you get used to it, you say, oh yeah, x1 is going to be equal to -2x2 when I move that over, minus 9x4 when I move that over. And then that's it. That's what that first line says. The other ones are 0. The coefficient of x3 is 0. Coefficient of x5 is 0. And then the constants are obviously 0. Okay, hopefully that wasn't too quick. Basically, x1 plus 2x2 plus 9x4. I'm moving the 2x2 over and then moving the 9x4 over by subtracting each one from both sides. That second equation is saying that x3 is equal to 3 times x4. That third equation, third row, okay, so first row gives me that, second row gives me that, last row gives me x5. What's it have to be equal to? Well, in this case, it has to be equal to 0, right? That's what, again, don't forget about that column of zeros to the right. That says x5 has to be equal to 0, and then there's nothing, obviously, in the last row. Now notice this gives me the x1, the first entry of my vector, that third entry of my vector, and the fifth entry of my vector if I'm going to write a general solution. Notice that here x2 is going to be a free variable, and over here x4 is going to be a free variable because those are not associated with pivot columns. So x2 and x4 are going to be free variables. You could put those at the end, but what I'm going to do is I'm going to put those sort of where they belong if I were to create a vector. So the second entry is free, and the fourth entry of the vector is free. Okay. Now, once we know this, now that we have our general form, this is the general form, we can go to the parametric form. This might get a little bit squashed on me, so let me make that slightly smaller. There we go. Hopefully you can read that. But the parametric form, since we have two free variables, we're going to end up with a parametric form with two vectors. Okay, one of them is going to be having coefficient x2. So we're going to have x2 times some vector. Now, the vector we're going to take is going to have, obviously, since we're going to have 5 entries, our vector in parametric form is going to have 5 entries. Next, our other free variable is x4. We're going to multiply that times some vector. And again, that vector is going to have 5 entries. So we put those down. All right, so bang, put those down, put the vectors. Now here's how we read off this first one. Coefficients of x2 is a -2 in the first entry. In the second entry, it's going to be coefficient of x2 is just 1 free variable. There's no x2 there, so we call that a 0. There's no x2 here, call that a 0. Whoops. And then there's no x2 here, so call that a 0. Okay? So the vector -2, 1, 0, 0, 0 is going to be the vector that's being multiplied by variable x2. As far as x4 goes, first entry is going to be -9. We're going to have 0 x4s in that second entry, 3, 1, whatever x4 is, coefficient there, and then 0, right? No coefficients to x4 there. So that would be the parametric form of the solution to the row-reduced echelon form of the matrix we had. So parametric form solution to that equation is in fact this one. So hopefully that gives you a general idea of both the homogeneous systems and how to write solutions in parametric form. Now, the reason we're looking at homogeneous systems is because they have a connection to the general solution, okay? So what I'd like you to do is take this system of linear equations, row reduce it using, obviously, the calculator, and find a general solution, find a parametric form. Well, let's just find a general solution right now, and then we'll go into parametric form in a minute. So find a general solution to this system of linear equations. Push pause on the video. All right, so hopefully you went ahead and did that. So we're going to create an augmented matrix. And because this is not a homogeneous, this does not have zeros here, we're going to have to create the entire we're going to have to create the entire augmented matrix. We have to make sure we have our constants on that right-hand side column before we row reduce. So I went ahead and did that. Okay. This system of linear equations translates into that augmented matrix here. You can always push pause if you're wondering about the matching up. And when you row reduce that, I got the following matrix. First row is 1, 0, 2, 3, 8. Second row is 0, 1, -1, 2, -5. And the third row is all zeros. Okay? Now, if you were going to create the general solution to this, you would say, well, x1 has to be equal to, again, well, actually, let me write this down first. x1 plus 2x3 plus 3x4 is equal to 8. Don't forget that, again, in this situation, this was the augmented matrix. We did have this this column of constant numbers, so don't forget about that. The second equation would give me x2 minus 1 x3 plus 2 x4 is equal to -5. And then because our third and fourth columns represented x3 and x4, and those two columns were not pivot columns, that means that those two variables are free variables. Okay. Now, just with a little bit of rewrite, I'm going to move the negative, excuse me, I'm going to subtract 2x3 from both sides of this equation. You can rewrite that as negative 2x3 minus 3x4 plus 8 on the right-hand side. Okay, be really careful about the minus positive things. The same thing with that second equation. If we add 1x3 and subtract 2x4 from both sides of the equation, what we're going to end up with is that 1x3 minus 2x4 minus 5. All right? Now you'll quickly notice, and this is that is the general form. I'll talk about the parametric form in just a second. But you should quickly notice that if we have those same exact equations, but instead of looking for a system, the solution where our constants are equal to non-zero numbers, if our constants are all equal to 0, well, the same process is going to go down. However, this last row, or this should be, I'm sorry, I misspoke. That last column will always be zeros. So we could literally copy and paste this if we were solving the homogeneous equation. Note what's going to happen here. So solving the homogeneous equation, this last entry is going to be a 0. Last entry is going to be a 0. Last entry is going to be a 0. And then here, because this is a linear combination of zeros, when you row reduce that, last column just keeps as zeros. Okay? I'll make that a little bit, oops, better. But they kind of misaligned here because some of the negative signs skewed things. But you see that last column is zeros, last column stays at zeros. And notice what happens. Basically, as far as the general solution goes, the general solution looks exactly the same mouse went a little bit haywire there. Except all those constants turn into zeros. Okay. Now think about what the parametric solution looks like to this. We have two free variables. So the parametric solution is going to look like x3 times a four-dimensional vector. We do this plus x4 multiplied times a four-dimensional vector. So a vector from R4. And what those vectors are going to be, well, they're going to have entries. Coefficient of x3 is going to be -2, 1, 1, 0. Hopefully that makes sense. -2 is coefficient x3 here. 1 is coefficient. x3 is this guy, so coefficient of x3 is just a 1, kind of the implied 1 out here. And then there's no x3 in this equation. Similarly, the coefficients of x4, -3, -2, 0, 0, and 1. Okay, so that is the parametric solution for the homogeneous equation. If we wanted to do a parametric solution for the non-homogeneous system, so scroll back up to here, what we would end up doing, that's hard to see. Let me create a new page here. All right, so now I've created a new page. There we go. So let me create a new page here. So this was our solution to the general form solution to the non-homogeneous equations. We had a couple of free variables, and then we had some constants. When we did the homogeneous equations, we had those exact same free variables, but we had no constants, so we could kind of leave this blank, any constant vector. Notice what this solution is going to look like here if we write it all in vector format. If we write it in vector format, basically all we have to do is add the constant vector, and I say the constant vector that we have here. So we'd have to add a four-dimensional vector, keep doing that, of 8, -5, 0, 0. And I claim that all of the solutions to that original non-homogeneous system are going to look like this. They're going to look like the 8, -5, 0, 0 entry. It's kind of like saying what would happen if you plugged in 0 for x3, 0 for x4. What would you end up with? You'd end up with that single vector as your solution in the case that x3 and x4 were both plugged in as 0. Okay? So the difference between the homogeneous system solution and the non-homogeneous system solution is just basically adding some constant vector. Again, this constant vector is the one that shows up in the row reduced echelon form of our matrix, not the one in our original matrix. Okay, so don't get that confused. The vector that shows up in solution is the one that is in the row reduced echelon form of the matrix, not the original matrix. So there you go. So that's the connection. That's how homogeneous systems of equations and the general systems of equations are connected. Okay? Now here's the way that this is stated formally. It says Suppose we have a matrix equation which we call AX equals B. And suppose that's consistent, that means has a solution, for some B, and let P be that solution. Okay, in other words, you can take A times P and give you B. All right, so P is a vector that you can plug in for X and make this equation true. Now, what are all the solutions going to look like? Well, all of the solutions are going to look like that P plus what we call VH, where VH are the solutions to the homogeneous equation. So that's how we state that formally. Basically, all that's saying is that when you write the parametric form of the solutions to a non-homogeneous system, it's going to look like this, the sum of the homogeneous system there plus another vector that works. So here, this 8, negative 5, 0, 0, that's the P that they're talking about. And then the VH, well, the VH is what you get when you add these two things together. Okay? So that's the connection to the general solutions. All parametric forms of the general solution are going to look like a solution to the homogeneous system plus a constant vector. And by the way, in and of itself, oops, in and of itself, we do state that this thing here is the parametric form. For the purposes of this class, we'll state that this is the parametric form of the solution. Okay, so if it's non-homogeneous, we still have parametric form. We just have one constant vector along with it. Okay. Also, if you go back to the very first example we did, you'll notice that same phenomenon. Our solutions, -2, -1, 1, plus a constant vector when the system was not homogeneous. Notice when it was homogeneous, we just had -2, -1, 1 without the constant vector added to it. All right. So that is the connection that we're talking about. Now, one thing that I wanted to do is I wanted to take a step back and instead of talking about specific matrices, I wanted to get a general sense about, just thinking logically through this and what pivot positions and free variables and how they're interconnected. So logically think through if certain homogeneous systems have non-trivial solutions based on the matrix A and just a couple of properties of matrix A specifically. All right, so let's determine if the equation has a non-trivial solution. Okay, hopefully this question is making sense. So if we have a matrix, and our matrix is a 3 by 3 matrix, and that matrix has 3 pivot positions, will this have a non-trivial solution? And then a second question is, if the matrix is 5 by 5 and has 3 pivot positions, will this have a non-trivial solution? let's think about this. Push pause on the video if you haven't yet, and think through how this is going to come up. All right, so I just copied that and pasted it on a Word document here so that we could look at it a little bit nicer. Okay, so the question is this. The first question, I should say, was this. Maybe that looks a little bad. Does AX equals 0 have a non-trivial solution if the matrix is 3 by 3 and has 3 pivot positions? Now, the way I do this is I think about, in general, what this is going to look like. So we have a 3 by 3 matrix. In order to have 3 pivot positions, when you row reduce it, it's going to have a 1 here, a 1 here, and a 1 here. Again, notice that matrix A is there. All of these would be pivot positions, so that forces us to have zeros above and below those pivot positions. Okay. Now, is that matrix, when you row reduce it, going to have a non-trivial solution? The answer is no. The only solution in that case is trivial, because think about, again, augmented matrix for the homogeneous system is going to have zeros over here on the right-hand column. And what this is telling us is that x1 has to be equal to 0, x2 has to be equal to 0, and x3 has to be equal to 0. So the only way to get a solution is to have x1, x2, and x3 all be 0. All right? So does it have a non-trivial solution? No. The only solution is the trivial one. All right? Now let's ask the same question. Does AX equals 0 have a non-trivial solution for that other statement? So now we're saying the matrix is 5 by 5 and has 3 pivot positions. In fact, let me do a page break real quick. Layout break. There we go. Now, if the matrix is 5 by 5, that means 5 columns there we go. And 5 rows. I screwed that up, but that's okay. We'll do that. Five columns, 5 rows. Now, it really doesn't matter where the 3 pivot positions are. If my pivot positions were here, here, and here, that means that these 2 rows would have to be all zeros, okay? Because I'm saying exactly 3 pivot positions. I'm not saying 3 or more. I'm saying we have 3 pivot positions. Notice that if I put them here, those pivot positions, zeros again would be above and below. That's going to leave me with 2 columns to be free variables. And again, we're going to have this augmented matrix. We're assuming that there's this column of zeros out here to the right. So basically, that gives me 2 free variables if I have 3 pivot positions. 2 free variables means I'm going to have infinitely many solutions. So I am going to have non-trivial solutions. So yes, we will have 2 free variables. So we will get non-trivial solutions. In fact, infinitely many of them. Okay. By the way, that is independent of where those pivot positions were. Okay. If you wanted your pivot positions to be here, let's say the 1-1 entry, or to me the first entry here in the first row, the third entry of the second row, and then the last entry of the third row. Again, notice we're just still going to have two free variables. They're going to be different variables. This time, the variable x2 and the variable x4 would have been free. And if you move your pivot position over here, now the variable x3 and x4 is free. If I were to move the pivot position here, now the variable x3 and x5 would have both been free. Okay? So no matter where you put them, if you have three pivot positions, that leaves you two free variables. So we get infinitely many solutions, therefore non-trivial solutions to the homogeneous equation. Now I want you to think through this on your own. We're going to ask the same question, but we're going to do a matrix which is 6 by 3 and a matrix which is 3 by 5, both of which have three pivot positions. I want you to determine if AX equals 0 will have a non-trivial solution. Go ahead and push pause on the video. All right, hopefully you went ahead and did that. Um, so what I like to do again is just think through this logically. Um, a lot of math is just doing that exact same thing and just thinking through a problem logically. Now the first thing we have to understand is, remember, if A is 6 by 3, that meant the dimensions were 6 rows and 3 columns. All right, so 6 rows and 3 columns and having 3 pivot positions. Well, if I have 3 pivot positions, it's going to look something like that, okay? Where zeros are below, zeros are above all of my pivot positions. Notice that since we had 3 columns and 3 pivot positions, that doesn't leave any room for free variables. So in the augmented matrix, if we'd included a column of zeros, we would not have had any free variables in our solutions. Okay, so does it have a non-trivial solution? The answer is no. There are no free variables. Okay, no free variables. Therefore, the only solution is going to be the trivial solution. Now, if we do the 3 by 5 matrix, well, very similar to last time, think about where the pivot positions could be. Again, 3 by 5 means 3 rows, 5 columns. So we're going to have this shape. If I put my pivot positions there, leaves me two free variables. Again, when I say put the pivot positions there, I am understanding that we're going to have zeros above and below them. And it wouldn't have mattered where I put my pivot positions. If I have 3 pivot positions, it's always going to leave 2 columns for my free variables. And again, this is the matrix A being reduced, not the augmented matrix. The augmented matrix would have another column of all zeros out here. Okay? So does it have a non-trivial solution? Yes, it has a non-trivial solution. It has infinitely many of them because the matrix will have free variables. The F form will have two free variables. Okay, hopefully that makes sense. Now, I'm going to ask one more logical question. Instead of dealing with AX equals 0 as a homogeneous system, let's ask ourselves, how about AX equals B? Let's ask ourselves, is there a way to get B no matter what value of B I choose? And then we'll think about this in terms of what we did in the matrix equations section of chapter 1. So go ahead and push pause on the video, read what the matrix is going to look like, how many pivot positions it has, and then in each case ask if we're going to be able to find a solution for every single B. Be careful, while it's a similar phrased question, the way you determine this is very different. It's not based on free variables, it's asking yourself, does it have a solution for each B? In other words, are there B's in which there's the no solution case going to pop up? And so if we think through these, let's start with the first one. So a matrix A is 4 by 5. That means 4 rows, 5 columns, and has 4 pivot positions. So if we have 4 pivot positions, imagine that there's zeros above and below. We are going to have a free variable, but that free variable is not going to impact whether or not I can get a solution. It impacts the fact that there's going to be infinitely many, but if we have equal to B over here, is there any situation in which we're going to have all zeros equaling a 1? And the answer is no, because each row is covered by one of the pivot positions. All right, so this matrix equation will have a solution for every single B. All right, now that in fact, there's going to be infinitely many solutions because we're going to end up with a free variable there. So, but we will have a solution for every single B. Now the next question says we have a 6 by 4 matrix that has 4 pivot positions. Now if it's a 6 by 4 matrix that has 4 pivot positions, those pivot positions are going to end up like that. And because we're going to have zeros above and below those pivot positions, that's going to give us 2 rows of zeros. Now remember, this is just the A part, right? The A is 6 by 4. Remember, when we augment, we're going to have some numbers over here on the right. So we're going to have another column of numbers. And it's going to be the case where we're going to end up with all a row of zeros. And there's going to be some possible way to get a number which is non-zero here, like 0, 0, 0, 0, 1. Okay, zeros, or the same thing isn't true in the last row as well. We're going to be able to get 0, 0, 0, 0, and then a 1. And so because of that, there are going to be some no solutions for various values of B. So does the equation have a solution for each B? No. There are some vectors for B, let me say for B, which will have no solution. Okay? So there are some vectors here that are going to wind up giving us a no solution case. And I didn't write out that first one. Let me write that out now. The answer is yes. Yes, there is no way to get a no solution case. Because we never have any rows of zeros. So that's kind of the typical types of logical questions you could ask about the relative size of the matrix, how that's going to row reduce, and if we know how many pivot positions there are, that leads us to telling us how many free variables there are, which again tells us all kinds of stuff. So that is it for this section. This section went fairly fast on my end, but be ready to go for the next section in a bit.